So we are going to evaluate this triple integral over where the E is the solid tetrahedron bounded by 0, 0, 0, and this plane. So this one is a little bit easier to draw than we have than the one that we did in the previous modules video. So I'm going to draw this, excuse me, by the usual approach. If I set z equals 0, I get the line 1 minus x. Looks like that. Where this is 0, 1, 0, and this over here is 1, 0, 0. If I set y equals 0, I get z equals 1 minus x. So that is a downward sloping line here. And the point above there, z equals 1 minus x, so 0, 0, 1. And if I set x equals 0, I solve for z, I get 1 minus y. So I would get this line over here. So my tetrahedron is then, or this plane is this part, just the top of it. And I'm being asked in this example to think of E as the solid bounded by x equals 0, y equals 0, z equals 0. These are all planes, and this other plane. So my tetrahedron includes this face, and then everything back here stops over here. So it's the solid that is made up by everything under this plane and above the xy plane and bounded by the xz plane, bounded by the yz plane, bounded by the xy plane. Okay, so that's E. And I want to find the volume of that, or sorry, I want to find the triple integral of the function z of that. Okay, so how are we going to set this up? Well, notice that we are integrating z. I can easily solve for z over here to get 1 minus x minus y. So this is exactly the situation that we were just talking about. I have an upper surface for z. You know, my tetrahedron stops at this plane, 1 plus x plus y plus z equals 1. My tetrahedron starts at this other plane, z equals 0. So those are my two bounding surfaces. So when I set up this integral over here, I've effectively set up the z bounds already. I'm integrating z from 0 to 1 minus x minus y. Great. And then I am left doing a double integral over the planar region that this z plane, you know, this one, projects down to. So let's draw that. What is the planar region that it projects down to? Well, you know, it's kind of embedded in here. It's this 1 minus x that we had gotten, y equals 1 minus x, going from y equals 1 all the way down to y equals 0 at x equals 1. And so we can use all this information and again think, should we do this integral as a type 1 plane region or a type 2 plane region? Again, in this case, if you have noticed by now, usually defaults to type 1 plane regions. We're more used to doing that. Certainly that was the case in Calculus 1. So therefore we have a lot more practice with that. So if I do type 1, then I'm thinking of x going from x equals 0 to x equals 1. And I draw a representative line, x equals constant. And then I see that x goes from y equals 0 to y equals 1 minus x. So those are my bounds for x. For y. So I'm going to put in here dy going from y equals 0 to y equals 1 minus x. So I'm just working now on the d version, the d portion of this integral. And then my x bounds I got here from x equals 0 to 1. That's my dx. Great. And then I'm just going to try to see if the iPad will let me kind of copy just this part. Let's see. Oh, I think it's going to work. Great. And it didn't quite fit, but you get the idea. So I have now set up my triple integral. As usual, I will do a little bit of this and then encourage you to calculate the rest of it as practice. I'm integrating z with respect to z. So that turns out really nicely to be z squared over 2 from 0 to 1 minus x minus y. And that leaves me with this expression of, I don't have to really put the 0 in there. I'm going to subtract 0 squared. So really I just have 1 minus x minus y squared over 2. Great. Add dy dz. Great. So at this point, we are back to the same types of double integrals that we have been solving in the previous lesson. There are all sorts of things you could do here. You could square this out and multiply things, and it'll get kind of ugly. Or you could try to integrate this by using the fact that for the y integral here, right, we are just integrating with respect to y. So x is a constant. So it's like if I was integrating 2 minus y squared, let's pick a different number, 3 minus y squared over 2. Same choices. You could multiply this out, or you could do a u substitution. You could say, oh, if u is 3 minus y, du is minus dy, and then do the integral that way. We have the same choice here. A very, very quick way to do the u substitution is to think of this integrand in the same way as 1 minus x minus y squared over 2 in the same u substitution way. If I integrate this, you might think 1 minus y minus x cubed over 3, and maybe some other negative sign somewhere. So, we don't know that yet, so we can take this expression and differentiate it with respect to y, a partial derivative. We would bring down the 3, the 2, and then times the derivative of the inside with respect to y, which would give us a negative 1. Okay, so we don't have that here, so we put it in. So this is, if you haven't seen this before, a quicker way to do a u substitution without going through all of the details of let u be this, and then du is minus dy, and then running through the substitution. So long story short, what I have just shown you is a very quick way to get to the next intermediate step, which is that this integrates to 1 minus x minus y cubed over 3 with a negative sign out front. And then we would substitute in y equals 0 to 1 minus x. And then we are left later to do that portion of the integral. Okay, so I have done enough here that I've shown you all of the new stuff, which is the space region E here, projecting down to a planar region where we decided this would be fairly easy to do as a type 1 plane region. We set that up this way, and then I showed you a little technique here that you can do a quick u substitution, even in this context where you're dealing with 2 variables. So you can continue this integration here and verify later that you get 1 over 24